Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 52, in which I will discuss some theorems on isomorphism. Now we prove a theorem. Theorem is phi is an isomorphism defined on a group G with given binary operation to another group G prime with given binary operation. Then phi inverse defined on group G prime with given binary operation to group G with given binary operation is also an isomorphism. Now we prove this. Let phi group G with given binary operation to G prime another group with given binary operation star is an isomorphism. Therefore, phi is a homomorphism. This is number one. Number two, phi is a bijective mapping. That is, phi is 1 1 onto mapping. Let this is group G with given binary operation O, and this is another group G prime with given binary operation star, and phi B a mapping. Here phi is an isomorphism. Let A, B belong to G. Here A belongs to G and B belongs to G. Image of A is phi A in G prime, and image of B is phi B. Since image of A and B phi A and phi B, that is phi A belongs to G prime and phi B belongs to G prime, and let phi A equal to A prime and phi B equal to B prime. Let phi A equal to A prime and phi B equal to B prime. Since phi is a bijective mapping, therefore phi inverse exists. Let this is number 1 and this is number 2. Therefore, from 1 and 2 we get phi inverse A prime equal to A and phi inverse B prime equal to B. This is number 3 and this is number 4. Now phi inverse A prime inverse A prime belongs to G. So here we take the binary operation O. Phi inverse B prime equal to phi inverse A prime is A and phi inverse B prime is B, implies that phi A star phi B, since phi is a homomorphism and phi A is A prime. Here we write A prime star phi B is B prime, using 1 and 2. Implies that phi inverse A prime star B prime equal to this phi inverse A prime operation phi inverse B prime. This is number 5. Therefore, from 5 we see that phi inverse is a homomorphism. Since phi is bijective, implies that phi inverse is bijective. From 6 and 7 we get phi number 1, phi inverse is homomorphism. Number 2, phi inverse is bijective. Therefore, phi inverse is an isomorphism defined on G prime with binary operation star to G group with binary operation O, that is phi inverse G prime with binary operation to G with binary operation O is an isomorphism. Proved. Now we prove the next theorem. Next theorem is, let phi be a mapping defined on a group G with given binary operation O to another group G prime with given binary operation O prime and mapping psi defined on G prime with given binary operation O prime to another group G double prime with binary operation O double prime be isomorphisms. These mappings are isomorphisms. Then composite mapping psi phi defined on group G with binary operation O to group G double prime with binary operation O double prime is also isomorphism. Now we prove this. Since given that phi is a mapping defined on G with given binary operation O to another group G prime with binary operation O prime and psi be another mapping defined on G prime group with binary operation O prime to another group G double prime with binary operation O double prime be isomorphisms. Therefore, number 1, phi and psi are homomorphisms. Number 2, phi and psi are bijective mappings. Let this is group G with given binary operation O. This is group G prime with given binary operation O prime, and this is G double prime group with binary operation O double prime. Phi is defined on G into G prime. Psi is defined on G prime to G double prime. Therefore, composite mapping psi phi is defined on G into G double prime. Since phi and psi are bijective mappings, then psi phi will be a bijective mapping. Here psi phi is defined on group G with binary operation O into group G double prime with binary operation O double prime. Let A be any two elements of G. Therefore, psi phi A operation B equal to psi phi A operation B. This is equal to psi phi is defined on G into G prime. So phi A operation B, here A, B and A operation B belongs to G. Its image is phi A operation B. Here its image is phi A and image of B is phi B. Since phi is a homomorphism, therefore here we get phi A operation. Here phi A belongs to G prime, so operation will be O prime. O prime phi B. Since phi is a homomorphism, and this equal to psi. Psi is defined on G prime into G double prime, and psi is also a homomorphism. Therefore here we will get psi phi A and image of psi is in G double prime. So here we will use the binary operation O double prime. So here O double prime binary operation psi phi B. Since psi is a homomorphism, and this will be equal to psi phi A operation double prime O psi phi B. Therefore psi phi A operation B equal to psi phi A operation O double prime psi phi B. Therefore psi phi is a homomorphism. Let this is number 1 and this is number 2. From 1 and 2 we get number 1, psi phi is a bijective mapping. Number 2, psi phi is a homomorphism. Therefore psi phi defined on G group G with binary operation O into G double prime with binary operation O double prime is an isomorphism. Proved. Now we prove another theorem. The relation isomorphism is an equivalence relation. For equivalence relation, we have to show number 1, reflexive property. Number 2, symmetric property. Number 3, transitive property. Number 1, reflexive. Let phi be a mapping defined on a group G with given binary operation into same group G with given binary operation as follow. That is, phi is defined on G with given binary operation into group G with same binary operation, such that phi x equal to x. Let this is number 1. Therefore, phi is identity mapping. We know that identity mapping is bijective. Therefore, phi is a bijective mapping. Bijective means 1-1 onto mapping. Let this is number 2. Let A, B belong to group G implies that phi A equal to A, phi B equal to B. Let this is number 3 and this is number 4. Again, by closure property, A operation B belongs to G. Now, phi A operation B, since phi x equal to x, therefore phi A operation B equal to A operation B. This equal to A means phi A and B means phi B. Using 3 and 4. This is number 5. Therefore, from 5 we get phi is a homomorphism. This is number 6. From 2 and 6 we get phi defined on G with given binary operation O to G with given binary operation O is an isomorphism. That is, phi is an isomorphism defined on G with given binary operation into same G with given binary operation. Therefore, phi is reflexive. Number 2, symmetric. Let phi defined on group G with given binary operation O into G prime with given binary operation O prime is an isomorphism. Implies that phi inverse defined on G prime with binary operation O prime into group G with binary operation O is also an isomorphism. Therefore, phi is symmetric. Number 3, transitive. Let phi defined on group G with binary operation O to group G prime with binary operation O prime and psi defined on group G prime with binary operation O prime to group G double prime with binary operation O double prime are isomorphism. Then we know that the composite mapping psi phi defined on group G with binary operation O to group G double prime with binary operation O double prime is an isomorphism. Therefore, isomorphism is transitive. Hence, isomorphism is reflexive, symmetric, and transitive. Implies that isomorphism is an equivalence relation. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.